Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
G'day everyone and welcome. As you would know, we're in the middle of starting to talk about probability theory, and we gave the axioms of probability. We did a few axiomatic derivations from those, which was to see a pattern of how you really prove something from the axioms. Now, having said that, we only use the axioms because we think they're a good model for real-world properties of probability. And they're very economical. Really, apart from saying that probabilities are greater than or equal to 0 and saying that the total probability of the sample space is 1, the only other thing you're saying is that if you have separate events, disjoint events, and you add them, you put them in a union, then the probabilities get added up. That's all that the axioms of probability say. So to some extent, it's surprising that we can derive all those other features from that. And we're going to be doing more derivation as time goes on. Okay, so we started talking about combinatorics, and we got up to talking about factorials and combinations, but I just want to revisit this MN rule for a moment, because in the context where the sample space is equally likely events, I would call it, MN rule is a funny name. I would say, or ordered pairs. So as we saw earlier. So, by the way, you may or may not know the word Cartesian product, which just refers to the set of ordered pairs. So the Cartesian product of sets, this sometimes quite often comes up, sets A and B, is the set, we call it A times B, or A cross B. So it's the Cartesian product of ordered pairs, and ordered pairs means it matters which order they're in. A comma B such that A is in A. It's all ordered pairs, and B is in B. That's all that an ordered pair means. And so the number of ordered pairs, because you're allowed to choose anything in A, anything in B, whichever item you choose in A has no effect on B, and vice versa. For each element of A, you get one element of B to choose, so that's B, and then you do that A times, so A times B. So if we're talking about the size of sets, that's absolute. I just write that with vertical bars like the absolute value. But the size of the set A times B is the size of the set A times the size of the set B. So that's not surprising. Remember that A 1, 2 is not the same as 2, 1. But of course, 1, 1 could hardly not be the same as 1, 1. So if they're two different elements, A and B, then there's two different orders in which you could put them. Okay, so that's the set of ordered pairs. So clearly that, and then the MN rule comes down to a fact about counting. The number of ordered pairs, A, B. So let's say we have some restriction we want to apply to A, and a restriction we want to apply to B. You're probably talking about not being able to see everything. Is that the question or another question? Yeah. Sorry, I'll try to keep that as visible as I can. Also, the lighting's not great. I'll do the best I can there. Okay, the number of ordered pairs A, B, such that, so say we're in some subset. A is in, I'll call it a subset A prime of A, and B is in B prime subset of B. So the key thing here is the restriction to A of the A element and the restriction of the B element don't relate to each other. The restriction is the same regardless of which A I choose, and the same regardless of which B I choose. Therefore, it is, of course, well, it's nothing other than the size of A prime times the size of B prime, because that's just an ordered pair in A prime cross B prime, which is, of course, size of A prime times size of B prime. So now I'm multiplying numbers. So the probability, if every outcome is equally likely, if every ordered pair, I can have to zoom out, pair is equally likely, of selecting. So I'll just call this good for short here, so that I don't have to repeat the definition. Good will just be the ones that are in the desired set A prime and the desired set B prime. A good pair is, A prime, very unsurprising, B prime divided by A times the size of B. In other words, which is equal to, if the proportion of the elements of A that are good times the proportion of the elements of B that are good over B that are good. So that's if every ordered pair is equally likely. There are A, B ordered pairs, and that's what it is. So this is the first iteration we'll see of the multiplicative rule for independent events. And in fact, when we later talk about independent events, the definition of independent events will be that the probability is multiplied. The independent events in this context are the first coordinate lies in, the first coordinate lies in A prime is the first independent events, and the second coordinate lies in B prime. So we'll do that more formally later. So they're independent because choose which A prime, which little a you chose have no effect on whether B is in B prime. Okay. So in general, the definition, we'll do more about this definition later. For any in any probability space, I'll remind you, a probability space requires us to have a sample space and also a probability measure. There's also a set of all events. I'll never emphasize that. So it's a probability space with a sample space and a probability function. Two events E and F are independent if the probability of both of them happening, which is an intersection, of course, probability of E intersect F equals probability of E times probability of F. That's just the definition of independent events. So we'll get back to that later. And I want you to hesitate before you extrapolate to many events. It's tempting to think that if you've got three events, they're independent if the probability of the three-way intersection, A intersect B intersect C, is equal to probability of A times probability of B times probability of C. Turns out that is a necessary but not sufficient condition. Right? To be independent three ways means effectively no information from any combination of the events can tell you anything about the other event. So we'll get to that later. It's more complicated for more than two events. So that's foreshadowing about independent events. We're going to talk a lot about independent events. But for the moment, I want to get back to the combinatorics, because doing the combinatorics is a key to actually being able to calculate these probabilities. So we've done the MN rule, which I prefer to call sort of product rule. We've talked about permutations, and that was kind of brief, but just as a reminder, I would normally use the word permutation for a full permutation, which is where you have all n elements in some order. And then the number of full permutations is n times n minus 1 times n minus 2, all the way down to 1, because n choices for the first, n minus 1 choices for the second. So those are full permutations. The number of them is just n factorial. And a partial permutation, I'd prefer to call it a partial permutation, is when you have only r out of n. And so when we use this notation PNR, it's not a very common notation, but that would be a partial, the number of partial permutations consisting of r objects out of n. And the way to find it, these formulas are easy to remember if you remember that we just have to order all n objects in any order, that's n factorial. But I've overcounted by a factor because the n minus r objects at the end shouldn't be included, so it doesn't matter which order they are. So I just for instance, if there were two objects at the end, x and y, that shouldn't be included in the partial permutation, I've counted it with x, y at the end. I've also counted it with y, x at the end. So every ordering of the n minus r objects at the end doesn't matter. I just divide by that overcounting factor. So that's the reason that's the number of permutations there. So now combinations, while a permutation or a partial permutation consisting of r objects is like select r objects and have them in an order that I care about, a combination is the same, but I don't care about the order. That's why it's an unordered collection of objects. So it's quite easy to go from the permutation to the combination to see, of course, if you have a permutation that's an ordered selection of objects, to get to the combination, I just forget the order of those objects. So that's, to get from a permutation to a combination, I forget the order. To go from a combination, which is an unordered selection, to a permutation, which is an ordered selection, I will then need to impose an order on the r objects that I have. There are r factorial ways of imposing that order. So ultimately, this theorem 7, before I get to the theorem, let me just remark on notation. There's too many ways. We say n choose r when we read this, n choose r. That's what this object is called. I like this parentheses notation with n on the top and r on the bottom. Note there is no fraction line because it's not a fraction. I like that because the numbers are large and easy to read, but there are other spots that you could put the n and the r that make these numbers a bit small. So that's n choose r. The key thing is I just want to know how many unordered combinations there are, and I know that the number of combinations, if I multiply it by r factorial, I must get the number of permutations. Because to get a permutation, you just find the combination and decide on the order of the r objects. So whatever this is, it has to be the number of permutations divided by r factorial. That's exactly what this formula is. Now you see, unlike npr, n choose r, which is sometimes called ncr, but n choose r is symmetric in r and n minus r. In other words, if you fix n and you swap r with n minus r, you get the same number. And it's easy to see because you're deciding which r objects out of the n you do include in your subset. There's a bijection of the subset to the complement. The complement would be which n minus r objects you do not choose. So, symmetric is another way of saying that n choose r. That's the number of ways of choosing the objects you include, r objects to include. It's the same way as choosing the n minus r objects which you exclude from the set. So you're having r yeses and n minus r no's, and it's the number of ways of doing that. Clearly, it's the same number of ways if you were to ask to do r no's and n minus r yeses. So that's this nice symmetry property of the combination. Another word of the number of combinations, you can call it n choose r, but the better name for it is binomial coefficient, because as you probably know, it occurs in the expansion of the binomial theorem. So let's go on a little bit. There's a lot of examples. Before we get on to all those examples and lattice paths, I just want to, since I've noted that it's called the binomial coefficient, the reason is that in the binomial theorem, it's a theorem, but it can be stated very simply. It's just a fact about algebra. I will state it in the case 1 plus x. You could do it for a plus b, but I'll state it for 1 plus x, because then I don't have to do powers of 1, is sum from r equals 0 to n. It's x to the power r. Clearly, when I expand this out, some of the terms, they'll have up to n factors of x. So they could have x to the 0, x to the 1, and so on, all the way up to x to the r. X to the n would be the highest expansion that I could have. Now, how many different ways can I select out r of them to be x? Well, if you think about expanding a product, you have to decide which, you select exactly one term from each factor. So I have 1 plus x, 1 plus x, 1 plus x. People sometimes prove this by induction and so on, which is perfectly valid, but might give less insight into what's going on. So let's just continue on here. So that was, we've already done basic probability, sample point method. And as I said, there is a tutorial this week, and you will have seen the tutorial posted on the website. The solutions will tend to go up at the end of the week. And we haven't learnt that many methods for evaluating probabilities so far, so you'll see that most of the exercises are either about the axioms of probability or just calculating simple probabilities with a sample point method. And as a simple reminder, if you're not quite sure what probability to assign each point, sometimes there's a number of choices you could argue for, but a simple choice is always to give each possible outcome the same probability. That would be, especially when you say we have no information about which object is chosen, or if you say that a certain method is completely randomized or completely uninformative, that would tell you that every possible outcome is equally likely. So that's what it means. So if in doubt, make them all equally likely, but sometimes they won't all be equally likely. So we've done the sample point stuff, we've done the axioms of probability, and those were the little consequences we did last time. Okay, let's get back to combinations and permutations. So, and we've had this theorem. So I just want you to remember n choose r and n choose n minus r. And actually this calculation formula, you will actually have to do some of these calculations by yourself. And while your calculator may or may not be able to do some of them, you see that in this form there's incredible cancellation because, of course, everything in the n minus r cancels with one of the factors in the n. So if you have a calculator, putting in this formula is a very naive and arguably poor way to calculate a binomial coefficient because you've got very large number divided by very large number. Now, it may be beyond the capacity of your calculator to cancel that correctly. It might give the wrong answer. Or even if it does, it might be outside the range of your calculator. So that's a very bad formula. This formula is somewhat better. Your calculator probably can do that usually. But there will, I guarantee you, well, it's a theorem, very easy to prove. We know that this is a whole number because it is a number of ways of choosing something. Right? A number of ways of choosing is by definition a whole number. Now we have proved that that equals this ratio. So therefore every factor, every prime factor that's in the denominator must cancel with one prime factor that's on the numerator. Therefore, before you actually plug in all the products in your calculator, you may well be able to do a lot of cancellation, and that will save effort. So not only that, but if you have, I like this formula, you could, but equally, you could do it the other way around, and one of those will have fewer factors than the other. So while it says, of course, numerator n minus 1, n minus r plus 1. This is what happens when you want r factors on the numerator and r factors on the denominator. Right? That has r on the numerator and r factors on the denominator. But if you were to calculate 10 choose 9, okay, something very simple. 10 choose 9 that way. You could use such a formula and then try to cancel. So 10, 9, 8, 7 down to 2, 9, 8, 7, 6 down to 1. But clearly I should have cancelled more. And so when the r is more than half of n, it's better simply to use the symmetry that we had at the start. So go straight from 10 choose 9 to 10 choose 1. It's better to do that than to struggle with formulas. So if you can pick between r and n minus r, pick the one that is smaller when you're calculating. Okay, and that is, of course, just 10. It's, I think it's worth bearing in mind. Some of these choose numbers are so simple that it's just worth remembering what they are without bothering with formulas. If I have to choose 0 objects out of n, how many ways to do it? One. Yeah. So, and by the way, remember that 0 factorial is always 1 as well. That's an important problem. 0 factorial is 1. You might think it shouldn't be defined, but you're just thinking selecting 0 objects. There's one way to do that. It's an empty one. So, and that makes perfect sense with all our formulas later. So just remember that one. N choose 1. If you have to choose one object out of n, someone tell me straight away. N, yeah, just choose which object. So some of them you don't even need to get into the algebra, you just remember the definition. I think it's worth remembering, you don't need to remember all of it, but n choose 2. This comes up so often. Yeah, of course we could just use the formula, n times n minus 1 over 2. So another way, okay, sometimes people are at half of n squared minus n. There are a number of ways you could write it, but that comes up all the time. It's also a triangular number. The triangular numbers are the n choose 2 numbers. So triangular number is 1 plus 2 plus 3 plus 4 plus 5. You'll find they're exactly the n choose 2 numbers. So anyway, those are the little calculations you might want to do. So 5 choose 3. If we're working it out straight away, of course, I would say, oh, well, 5 choose 2 is easier to work out. So 5 times 4 divided by 2, 10, isn't it? Yeah, 5 times 2. So then, this is also a good way to check if you're actually writing out sample points, which, by the way, overall I don't invite writing out sample points because usually it's wasted effort, but it's kind of a babyish way to do things. If you are writing them out, then you can just double check the number of combinations to be sure you haven't missed anything. That's a good check. Because, you know. Okay, so, sorry, okay. So, number of ways of choosing. Okay, select 5 ways randomly from 12 people. By the way, when we say select 5 randomly from 12, that's an example of what I said before. Whenever the word randomly or particularly uniformly at random comes up, that's a particularly common phrase. The word uniformly at random means every possibility has equal probability. And therefore, the number of possibilities is the number of ways of choosing 5 people from 12, which is 792, turns out. And then, if you want to have a committee that does contain the 2 oldest people, we know those 2 people, they're fixed people, and then from the 10 remaining people, I only have 5 remaining to select. So that's 10 choose 5. Sorry, 5 total, so 3 remaining to choose. By the way, you'll notice equivalently I could have selected the 7 that are not on the committee. So that would be 12 choose 7 divided by selecting the 7 not on the committee from 10, who are not the oldest 2. The youngest 10. That would be equivalently 12 choose 7 divided by 10 choose 7. You see it's the same number. So I just have to do 120 divided by 792. Once again, there's going to be big cancellation whenever you do this. 5 out of 33. So now if I want to choose 2 separate committees from 15 people, how many pairs of committees? So let me first misdirect you. I have to check select 2 committees totally separately, right? So there's nothing to do with them. So I'll use the A-B rule, the product of not even probabilities. I'll just use the product of number of committees. So, 15 choose 3 times 15 choose 4. Is that correct? It's not correct. And can someone elaborate? Why do you think it's not correct? Yeah?
Is it because 3 people already
Yeah, exactly. The 3 people that have already been chosen should, according to our interpretation, not be selected in the 4th committee. So part of it is a linguistic difficulty with the word separate, because arguably if you said they were chosen separately, that might mean something different. If I choose a committee of 3 and then separately choose a committee, then the choosing is the thing that is separate. I choose one and then separately choose another. Then they might overlap because I wouldn't know. But this is different. The committees are to be separate. So if it had said separately chosen or chosen independently, particularly, I would err towards the other interpretation. But here it says separate committees. That has no interpretation other than that the committees have to be disjoint. So now it's not a matter of multiplying the number of possibilities. Then you just have to count how many that are size 3 and 4. So, okay, here's a second attempt. That means I have to select 7, right, out of the total to be on the committee. So it's 15 choose 7. Is that correct? Is it correct to say that I have 15 choose 7? You see, there's a lot of blind alleys you can go down here. And that was not really a blind alley, but you have to do more work. What's wrong with saying, I need a committee of size 3 and 4, so let's just pick 7 people from 15? What's wrong with that?
Because you can arrange them differently in the 2 committees.
Yeah, then I would know the union of the committees. I would know the 7 people that are on a committee, but I wouldn't know which committee each of those 7 people was on. But that suggests that it's a partially correct solution. So rather than doing the solution on the page, let's just try another method that suggests itself to me. First, choose the 7 people that are on the committee, right? So I have to choose 15, choose 7. And then I have to choose which of those are in the 3 committee and which are in the 4 committee. Once I know who's in the 3 committee, I know who's in the 4. That's much like the normal thing. So once I know that, I have those 7 people. Now, I don't, it could be any 7 people, but let's just label them 1 to 7. And if you're worried about the probability of actually labeling them 1 to 7, there's nothing wrong with giving a fixed order to an unknown subset. The reason there's no problem with that is because you could order them, for instance, alphabetically, or you could order them by birthday. It doesn't matter. There's no problem. Like, I have 15 people. Let's say they're labelled letters A to O, O is the 15th letter. I could label my people A to O. Then I wouldn't know which of the 15 letters I had chosen. I have 7 letters. But there's nothing wrong with saying, okay, first letter, then second letter in order of alphabetical. There's nothing wrong with that. Right? So I even though I don't know exactly which 7 were chosen, I still can label them. First guy to 7th guy in an unambiguous fashion. Then from those 7, I have to choose in that unambiguous order. I'll pick 3 of those 7 will be in the first committee, and 4 of the 7 will be in the second. Now, once I know which are in the first committee, I don't need to choose the second. It's automatic. If you wanted to be pedantic, there's no need to do this at all, but you could say, oh, now there are 4 people left over, of which all 4 have to be in the second committee. So, but of course, that's multiplied by 1. So I wouldn't bother doing it. But if you're really thinking, okay, let's select 7 for any committee at all, then 3 for the first, and then 4 for the second. So now, when I do 15, choose 7, I'm going to do 15, 14, 13, 12, 11, 10. So I have to have 7 numbers on the top, 9. On the bottom, I'll have 7 at 7, 6, 5, 4, 3, 2, 1. So that's the first factor. Then the second one, I have to do 7, 2, 3. 7, so that means 3 factors on the top. 7, 6, 5, 3, 2, 1, right? Because it's always 3 factors on the top, 3 factors on the bottom if I'm choosing 3. So I can even cancel this. The 7, 6, and 5 will cancel with the 7, 6, and 5 there. There's probably more cancellation that you could do. Let's just see. Obviously, on the slide, it tells you a totally different way to evaluate it. You can have 15 choose 3 for the first committee, and once you've done that, there's 12 choose 4 for the second. So, because if I don't choose the 7 total, if I just choose the first committee 4, there's still a non-trivial choice of who are in the second committee of 4. So that would be 15 choose 3, 12 choose 4. Let me just, that's actually a bit nicer because I have less down the bottom. So 15 choose 3 times 12 choose 4. By the way, it has to be the same if I do it 15 choose 4, 12 choose 3, because it doesn't matter which committee I'm choosing first. So that would be 15, 14, 13, 3, 2, 1. And then I have to do 12, 11, 10, 9, 4, 3, 2, 1. So you can see, after not much cancellation, you see that even the formula is the same, not just the final number is the same. So in general, for successive choosing problems, there will often be many, many orders in which you could do things. So long as you have valid reasoning, you'll get the same number otherwise. Okay. That's an example of choosing pairs of committees. Now, okay. Is that okay? So note 1 is actually the same thing as I just suggested, except in the other order. So that's ways of choosing committees. So this is a whole general way of thinking about this called multinomial coefficients. It turns out what we just did is called a multinomial coefficient. And there's another way of writing it. So I could have called that, I have to choose 15 objects. Out of 15, I have to choose a partitioning of the 15 into either committee 1, committee 2, or no committee at all. The ways of choosing that is these are all binomial coefficients, but certain products of binomial coefficients are called multinomial coefficients. So 15 choose 3 for the first committee, 4 for the second committee, and 8 to be neither committee. So, and I think they're right, 15 choose 3, 4, 8. Okay, I put commas. I think it can be nice to put commas, because I have multiple to do. The condition for a multinomial coefficient is that R1 up to Rk should add up to n. Otherwise, it's not clear what it is about. You're dividing a set of n elements into not just yes or no. It's called binomial coefficient when you're dividing into yes or no, because there's 2 options, yes or no. Multinomials when you're dividing them into k categories, not just one category. And every multinomial coefficient can be got as a product of binomial coefficients, because it's just, and in many different orders, By the way, in case you're wondering how this 7 came here, 15 choose 7 is of course the same as 15 choose 8. So choosing the 7 that are on the committee is the same as choosing the 8 that are not on the committee. It's the same choice. So you can do a multinomial coefficient by first doing 15 choose 8, and then 8 are gone, and what's left over is 7. From there we have to choose 3, and then what's left over is 4, and we have to choose 4 from 4. So it's always a product of binomial coefficients, and you can do it in many orders to get the same. There was a question, I think. Maybe not. Okay, so multinomial coefficients. Okay, well, note 4. Okay, I said you should always have them adding up to n. If they add up to less than n, well, a convention you could say is I want k groups, but then there'll be a leftover group. It's just adding a group number k plus 1 that doesn't have any object in it. It has the object that were left over. So if you wanted to choose k groups that don't add up to the total, then you just put in an extra group that makes it add up to the total. So with that convention, it's the same as binomial coefficient. You're doing 7 choose 3, but that's the same as 7 choose 3 and 4. The 4 is whatever's left over. Okay, yeah, so that's what they say here. Binomial are short for those particular multinomial coefficients. Now, I don't know why the word multinomial coefficient doesn't appear on this slide, but that's the name. Multi meaning 2 or more. You know, it works for 2, but it works for more. I really want to say the multinomial theorem. So, okay, my luck has returned. So let me state the multinomial theorem in the context of that slide. Yeah. I could write it totally separately, but I think since we've just been writing about it here, I'll just put it as an annotation at the bottom. Because there's a reason that this is called a multinomial coefficient. Okay. Well, the multinomial theorem, it won't be too surprising to you. Instead of 1 plus x, I'm just going to do it with general variables x1, because there's going to be a certain number of k variables, x2, x3, up to xk. And I don't know why I put commas, because actually what I want to do, much like the original binomial theorem, is I want to do a sum of it. If you had a difference, you would just put a minus sign in the associated variable, so that's not very hard. But I'll just assume they're all pluses. If I want to raise that to a power n, it's actually the sum, and unfortunately the sum becomes more unpleasant than before, because when we were doing the binomial theorem, you would remember that I was allowed to say, oh, I don't know how I failed to put that in. Okay, so let's put it in. N choose r. You have to, of course, in that context it was 1 plus x to the power n. I had to, of course, choose exactly r out of the terms to pick an x from, and the remainder of the terms you would pick an r, a 1 from. So x to the r, n choose r. So that's what the binomial theorem said. Multinomial, by the way, this formula is called a multinomial. And then the expansion of the multinomial power is no longer can I just say r goes from 0 to n, because I have to have a certain number r1, and I also have, that's r1 will be the number of x1s. I have to have r2, x2s, and so on. Up to r. So all of these are integers. You might not think that the summation notation means that these are integers, but it sort of goes without saying. It's rare to sum over indices that are not whole numbers. So they're going to be whole numbers, they're greater than or equal to 0. But there is one more constraint. I don't just sum over all sum. What's the extra constraint? You can think about it this way. The term that's going to be added is x1 to the power r1. So that's how many x1s I pick. x2 to the power r2. xk to the power rk. So that I picked r1 x1s, r2 x2s, rk xk's, and all of that came out of raising that to the power n. So there's certainly a constraint on the ri's altogether. Yep, it's exactly right. This is a term that occurred when you expanded n factors together. Each factor gave you one power of some xi. So however many powers of xi's all put together, r1 plus r2 up to rk, it better be n, because there were n factors. So that is the constraint here. r1 plus r2 plus rk equals n. Okay, and so that term doesn't just appear once, except for certain special cases. In general, you have n factors to choose from. From those factors, I have to choose r1 of them to be allocated to the first variable, r2 to allocate it to the second variable, and so on. So r1, r2, up to rk. And this is a multinomial coefficient, in case anyone thought I was multiplying. So this is, sorry, that's a bit of a, so there you go. That's what the multinomial theorem says. You have n, you choose how many of the first guy, how many of the, up to how many of the k variable, and then that's the number of ways that you get that particular term. So it's a theorem in algebra. The coefficients in it are called multinomial coefficients, and they can be expressed as products of binomial coefficients. So let's continue with these examples. You might think it's boring to do a lot of examples, and sometimes it is, but for these ones I think there'll be some subtleties that you might pick up on by learning these. So we did those committees. Yeah, we've done the committees. So let's now talk about probability of getting 2 heads on 5 tosses of a coin. Well, this is not that hard. Okay, so don't do sample point. Also, there's a typo because there's 5 tosses. So wait, oh no, it's not a typo. It's just my. It's hard to see how many H's. Yeah, there are 5 H's or T's. So there are 32 equally likely strings, like strings in the letters H and T, of which how many strings have 2 heads? So there's 2 ways of thinking about it. One is that you've got a set of 5 coins, and I sort of know they're distinct coins. So just I do them in a certain order. How many different ways are there to pick 2 of them to be the heads? That's 5 choose 2. Another way to think about it is the word. The word just says for the coins done in a row, how many of those words have 2 H's and 3 T's? It's the same question. It's 5 choose 2. In case you're thinking, oh, but surely a head and a tail should be equally likely to a head and a head because heads and tails are the same. That's not the case because although you might not care which order the coins are thrown in, or even there can be imposed an order on coins. That's what I was saying before. Any set of distinct objects, you can impose an order of them arbitrarily. And then head and tail and head are distinct outcomes, whereas head and head are the same outcomes. So, the point is, you do need to know how many out of the total. Head tail is not the same probability as head if you don't care about order. Okay, so so 10 out of 10 out of 32, 5, 16. That's the number of ways of doing it. Bijection principle. Now this has gone without saying, I would say, but what is a bijection? A bijection, and a synonym is one-to-one correspondence. So if there's a bijection between sets A and B, that's saying that for every element of A, there corresponds a specific element of B, and the other way around, for every element of B, there corresponds a specific element of A. And it's, for that to be a one-to-one correspondence, you should really get back to the same, it should be an inverse operation. So you should be able to say, from an element of A, give me an element of B, and from that element of B, you should be able to invert it and give me back the same element of A. It turns out if there are, even if it doesn't give you back the same element of A, if there is an injective function from A to B, and there is an injective function from B to A, then they do have the same size. But the word one-to-one correspondence really means that you can invert it in a specific way. So if there's a bijection, then they have the same number of elements. Simple observation that you can pair them up one by one, so you count them at the same time. So let's illustrate that. And by the way, that's what I was just talking about. This is a string interpretation of binomial coefficients. How many strings in 2 letters have 2 H's? So because I didn't the multinomial coefficient, it's worth talking about the string interpretation. And I don't mean string theory, I mean strings of letters. Multinomial coefficient. Once again, n, choose R1, R2, up to Rk, is equal to the number of strings in k letters, okay, having R1, by the way, what are the letters? I'll just call them Li, okay? R1, L1s, R2, L2s, R3, L3s. Like L, I'm just, so that I don't have to say ABC without knowing where it ends. And up to RK, LK. So if the letters were ABC, it would be R1As, R2Bs, and R3Cs. So a binomial coefficient is how many strings, or, by the way, and if you don't like the word strings, you could use the word words. Sometimes, but they don't have to be English words. They could just be any words in K letters. And the one thing I forgot to say there was the strings have to have a fixed length. Right? If I allow length, arbitrary length, there will be infinitely many. So it has to be, sorry that I forgot to say that, it has to be length and string. So the first example of the bijection principle that I'll emphasize is that a string in K letters is in bijection with a partition of an element set into K groups. The letters become the groups. It's like having, how do you do it? You get your group, imagine it's a group of people, and you just assign each person a letter. And then, you assign each person, you just write all the people in order, and you assign each group a letter. So an assignment of people to groups is the same as just putting a letter on each person, which is the same as having a word of n letters, and each letter has to tell you which group that person went into. So both for multinomial coefficients and binomial coefficients, this is quite a powerful bijection between assignments of people to groups and words in K letters, where K is the number of groups. Okay, so for two groups you get binomial coefficients, the groups being head or tail. Okay, another illustration of the bijection principle. Count the number of ways that 3 identical rings can get arranged on 5 fingers of one hand. Each finger can have any number of rings. Now, so this actually, I'm even going to give a name to this in advance because I want to explain the principle maybe a different way later. So, I call this either the supermarket principle or supermarket method. Let me call it the supermarket method. It's not even deep enough to arrive to the level of a principle. So, bijection principle is totally general. Whenever you have a bijection between two sets, you know they have the same number of elements. But this example of it is the supermarket method. Applies to this example, and I'll explain more generally what I mean by supermarket method later. But I have 3 rings. They have to be arranged on 5 fingers of one hand. But the problem is that I could have 0 rings on one finger. Right? It's not like every finger gets a ring. And also some fingers could get multiple rings. So there's a suggestive bijection here. Now we've got 3 O's. O is meant to be a ring. Right? Whenever you think in terms of strings of letters or words, that can be a powerful technique for getting an exact bijection or an exact interpretation of what's going on. So if I have these 3 rings, I have 5 fingers, and the bijection that we're going to think up is saying, well, I have to have 3 rings, and O is going to mean put a ring on. And then what do you think the plus means in this bijection? If I have 0, 0, 0, plus, 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 plus. One ring, sorry, did you say one finger with 3 rings?
Yes.
And then 4 fingers with no rings? Yeah, so So there's one finger with 3 rings and four fingers with no ring. So why do I have 4 pluses instead of 5s? What do the pluses mean? How did you get this idea? I mean, yeah? Yeah, spacer is a good idea. It's sort of like a spacer, or it's like a return on a typewriter. You know, go to the next one. So that's so in terms of the supermarket method, let's imagine instead of rings and fingers, they were apples and customers. So you know, let me make them oranges because they look a lot more like rings. Okay. So when I draw them, so 3 oranges and 5 customers. Okay, so this always makes it easy for me to remember the method, right? So they're all coming on the conveyor belt, and you know, so this is the conveyor belt, and then above. So I have to do my 3 oranges, but I don't know how many. The question is, how many ways could I have those 3 oranges? I have 5 customers. So this is kind of a funny example because it's obviously a shop that doesn't mind customers coming to the till and buying nothing. So they just go there and say hello. So some of the customers clearly will not be buying any oranges. Be that as it may, so one way that would be for the first customer to have all 3 oranges and then the remaining customers. By the way, here is the cashier. I'll put them at this end because then I want the strings to be in this kind of order to make sense. So let me do 2 rings on finger 1 and 1 ring on finger 4. That's the same as having 2 oranges belonging to the first customer. Then, so my pluses will be my dividers. So what is a plus over there? I'll draw as a little supermarket divider. So you see, the key point is with 5 customers, I only need 4 dividers. Right? There would be no point to a 5th divider because that would mean go on to the next customer. In fact, if I had a 5th divider and I had an orange after the 5th divider, who'd be buying that orange? No one. I should, if I have 5 dividers, I should have 6 customers. So in moral of the story, to assign a certain number of objects to a certain number of groups, but not requiring, like I have these oranges, I have to assign the oranges to groups, but the thing is, it's not like orange 1, orange 2, and orange 3. If I had, or to be more concrete about it, if I had an orange, an apple, and a plum, that would be quite different. I would have to assign the orange, apple, and the plum to 5 people. I would just say, well, the orange has to go to 1 of 5 people, the apple has to go to 1 of 5 people, and the plum has to go to 1 of 5 people. So that would be 5 cubed. That would be an MN rule. The reason this is not an MN rule is because I don't care about the difference between orange 1 going to customer A and orange 2 going to customer B versus having the oranges swapped. The oranges are not distinct. So you have to use the supermarket method when you have indistinct objects to be allocated. Indistinct objects. If your objects are all distinct to allocate, then it's very easy. You just take that first distinct object, say who gets it. Second distinct object, who gets it. So when you have indistinct objects, you use the supermarket method. Here, when you're talking about rings on fingers, it's the same. You have 3 indistinct rings. It would be quite different if you had a gold ring, a silver ring, and an engagement ring. Then it would be, once again, 3, 5 to the power 3. So the number when they're indistinct is far lower, because of course, when they're indistinct, you just gel them all. So what counts as multiple distinct ring allocations is just a single indistinct allocation. So you use the supermarket method when you have indistinct objects, and you can see how that works. 3 oranges and 5 customers. So 5 customers, that implies 4 dividers. So the little triangles I've got on the right here are dividers, and they correspond to the pluses. And the plus means nothing other than move to the next finger, catching, that kind of thing. So, so you mustn't have 5 dividers because otherwise it wouldn't be a bijection if you had 5 dividers. Some of the things would not be meaningful because they would have an orange past the 5th divider. Having just said that, I can find a way to make it. So, by the way, what is the number is, of course, I still have to count the number of arrangements, which is 3 plus 4, choose 4, because there's 3 oranges and 4 dividers, and I have to choose which of them are the oranges and which are the dividers. Once I know which of them are the oranges and which are the dividers, I know exactly which